we're going to talk about. Today we're going to good afternoon, everyone. Today we're going to be talking about thank you for attending. Today we're going to be talking about the concrete from classic to high performance. This webinar is very interesting in a way that it gives you some kind of overview about the concrete from very beginning to at latest state of the art about the concrete. It's very interesting even for those who have very high extensive experience with concrete. They might find it interesting. And let me introduce myself before I start. I'm a professor of civil engineering. I've been teaching for over 40 years. I've been teaching, if you can guess it right, I've been teaching concrete design and concrete as a material. And I've been teaching steel design and construction project planning and scheduling and construction management. Today's webinar, like I said, it is very interesting. We have many slides than we can cover in about a couple of hours. So some of the slides I'm going to go over very quick. Because we hopefully we can reach the end of the slides, and we'll finish about a few minutes before 4 o'clock Eastern time. I'm going to leave about 10 minutes or more somehow for question and answer. In the meantime, if you want to contact me, you can send me a chat message. I already opened chat message. You can send the questions, or I can answer the question. If you want to contribute, you're welcome to do that. And let's get started. Today's webinar is about concrete. Concrete is basically, we're going to start from beginning about the concrete. What is a concrete? And from very beginning, for those of you who have never heard of concrete, probably they find it kind of redundant. Concrete ingredients. What the concrete is? We make concrete is a man-made rock. The concrete is a magical material, by the way. If you look at it this way, concrete is a magical material, absolutely magical material that we can, at room temperature, add water, and all of a sudden you're making rock. Show me any other material you can do it with other than concrete. Concrete, it is a classical material. It is the contemporary material. It is the future material. One more thing. Concrete is the second most consumed material on Earth after water. Concrete is not only, it's just kind of a material that we use for design. Concrete can be used as a projection of the future, as a measurement of prosperity, as a measurement of civilization, as a measurement of power, because most of the countries that want to show the power, they show mega structures made of concrete. That's why it's a challenge. It is a simple material, but yet very complicated. It is the classical material, but yet it is contemporary. It is a homogeneous material, but yet it is heterogeneous material. It is the material of all kind of contradiction. It is the present materials and the future material. Now, what we're going to talk about today is basically overview about the concrete from the very beginning. What's the concrete? The classical, we're going to start from the classical traditional concrete that everybody knows, and most likely you guys who are graduated maybe recently, you already have seen some of this information in books, and then we're going to transition to the concrete, the contemporary concrete that you haven't seen it in book. It's not even published in books and papers. That's why we're going to discover the whole spectrum of concrete as a material. How we make it is very simple. The thing that is very interesting about concrete that it is everywhere. Nobody can monopolize on a concrete. The ingredient of concrete is available in every corner of this planet. It's made of aggregate. We call it aggregate here, fine aggregate and coarse aggregate. And the division here, the separation between fine aggregate and coarse aggregate is sieve number 4. So the material that's mostly retained on sieve number 4 is, in this case, coarse aggregate. The material that is mostly passing number 4 and retained on number 200 is fine aggregate. So aggregate is very cheap. Now, aggregate can be a mineral aggregate, or aggregate can be anything. It can be recycled concrete, it can be recycled rubber, it can be glass, it can be aggregate. Doesn't mean that you have to have sedimentary rocks from here and there. It can be anything that we mix. and as part of the mix design. Now, this is very cheap. I'm telling you that aggregate is everywhere. Dig in the ground and you can get aggregate. Okay? Go, you have some quarry on the mountain and get aggregate. But the next ingredient is cement. Cement is mostly, we can use Portland cement, and cement is the most expensive ingredient of the concrete. The reason for that is because we invest a lot of energy to produce the cement. Not because the ingredient of cement is rare. No, the ingredient of cement is also available everywhere. It is like a dirt cheap kind of ingredient. But the problem is that we have to invest in these dirt cheap materials, puts on some energy to produce a chemically balanced material. So the money I'm spending on the energy to transform this ingredient into another kind of material that has somehow an energy saved in the chemical composition of that material. And guess what? Water, I mean, nobody paid for money for water. Water is available everywhere, right? Other than drinking water. And we are lucky here that we can get water from everywhere. It rains water, right? Or we can dig in the ground, you can get water. And so that's why this is also available everywhere. Sometimes, you can have air already in the mix, or sometimes what we do is that we add some kind of detergent in order to produce bubble in the concrete. We call it air entraining agent as an admixture to improve the performance of all the classical concrete in face of the weather, in face of challenges, in face of the pressure in the concrete to absorb the pressure due to either osmotic pressure due to icing, or due to the hydraulic pressure due to the expansion of the water in the concrete, or any alkali pressure or any kind of pressure in the concrete. So the best way to handle this one is basically produce bubbles to absorb this kind of pressure. Now, from here to here, you can say this is a classical, common, basic ingredient. But if you want to improve on the ingredients, so what you're going to do is you're going to add admixtures. Adding admixtures, what it does, sometimes it alters the property. It alters the properties. Make sense? Alter property of the concrete of the standard. So sometimes these kind of chemicals or materials that we add, we call admixtures, or we added additive, call it whatever you call it, to alter the behavior of the concrete. Now, aggregate is approximately 70% of the concrete is aggregate. So that's why aggregate is important. It's extremely important in a way that in a concrete design mix, in this case, you focus on an aggregate. The strength of aggregate is become relevant. The stability of aggregate become relevant. And the gradation of aggregate become relevant. Relevant to what? To the final product of the concrete that I'm looking for. I'm looking for a good quality concrete. I'm looking at stable concrete. I'm looking at durable concrete. I'm looking at a stronger concrete. So that's why the aggregate is the one that is most important kind of ingredient that I need to look into, because it's approximately 70% of the or more of the aggregate is made of the concrete made of aggregate. The aggregate has effect, I mean, on its effect on workability, its effect on stability of the concrete. When we say stability, that means whenever we start with a mix, we end up with a good mix. But whenever we start with the mix and all of a sudden ingredients start to separate, right, in the different corners, that means we have unstable kind of concrete. Drainage, we already talked about the pressure in the concrete, that sometimes the well-drained concrete will have less pressure, survive longer under severe circumstances. The frost resistance, which is the physical and any other thing that we can maybe relate, including the economy. Nowadays, if you can produce concrete cheaper, one penny, if you can produce a concrete with 1 penny cheaper, then you survive. If you cannot, that means somebody else will gonna eat your lunch. That's why it is important for us to focus on everything. Nowadays, the challenge is great. The challenge typically is great. And when we mix concrete, we mix it how? We have a coarse aggregate and fine aggregate. Makes sense. Coarse aggregate, like I said, that the dividing line between coarse aggregate and fine aggregate is sieve number 4. Sieve number 4 meaning that it is 4 opening per inch. Makes sense. We have 4 opening per inch. They can tell about more or less. This is less than, slightly less than quarter of an inch each opening. So this kind of proportioning between fine aggregate makes a big difference. In other words, if you have to have a mixed design, then most of the strength of the concrete made of because of the contact of the coarse aggregate to coarse aggregate. That about 80% of the strength comes from the coarse aggregate to coarse aggregate friction. Now, in this case, if the fine aggregate will contribute for the rest of that, which is 20%. Now, if you can have options in how much fine aggregate I can afford or I can use in a mix, try to be on the lower end of it. That means do not exceed, the maximum. To be on the safe side, use less fine than needed to fill the void. The reason for that is because overfilling the here it is overfilling. If you can see this, overfilling, it means that you already causing damage to the concrete. You're already separating the coarse aggregate from each other. You're already minimizing the strength of the concrete, because like I said, this gives you 20% of the strength because you have too much fine aggregate, right? So most of the strength comes from coarse aggregate to coarse aggregate friction. Makes sense, which is bonded here by the paste. This is where the strength of concrete comes. If you add too much fine, then you are actually separating the coarse aggregate, from each other, and that will reduce the strength substantially. To be on the safe side, if you have aggregate with no fine, that means you talk about here the strength is approximately 80% of the maximum we can get, and 80% is a good substantial. And this concrete that you produce with little or no fine, that is classified as well-drained concrete, a concrete that will survive under many pressure inside interior pressure, which is hydraulic, osmotic, and all kind of pressures. Now, the best design mix, if you fill up, use the fine aggregate enough, just enough to fill the void between the big particles, and that will give you, in this case, the best that gives you 100% of the strength or potentially strength of the concrete. So here it is. The key word is you can use fine aggregate enough to fill the void between the big particles. Less is not really good. More is not really good. But to be on the safe side, less is better than more. Okay, so this is something that you probably keep in mind here. This is a classical theory. Now, another thing that you probably need to look into it, which is in this case, how the freezing thawing happened. The freezing thawing and the cracks in the concrete and accelerated damage to the concrete, it happens because the aggregate itself has some pores in it. They have some pores in here, and these pores will be filled with water. And water will expand approximately, it will expand 10% approximately of its volume when it freezes. When the water freezes, unlike other materials, water, when it freezes, it will expand approximately 9%, 10%. And if it want to expand, it needs volume, it needs space. And that's why if it doesn't have a space here, if the aggregate is fully saturated, if the aggregate is completely saturated, and this water, subjected to freezing, so what can happen is it's going to push against the paste, and that will create a crack. So the problem is that if you have an aggregate like this here, and you have another aggregate somewhere here beside it, and another aggregate somewhere here, right? Look what happened. If there's a pressure here pushing against the paste, it will create a crack. And if the other aggregate has the same kind of problem, so this kind of crack will somehow, you see that? This crack will join each other. So we'll end up with a cracked concrete of it all over, and that would cause deterioration, and rapid deterioration, accelerated deterioration of the concrete due to the freezing thawing problem. Freezing thawing problem, water. The problem is water. water expand when it freezes. Now, what happened is that if there's a room here, that's, imagine if there's a bubble, air bubble in the concrete itself, and this crack hit the air bubble, then it stops. So what the air bubble do in this case, the air bubble will absorb this kind of energy, will absorb this kind of crack, will stop the crack. And that's why we, in this case, ask, in case if the concrete is subjected to the weather and outside, we ask for approximately 5% to 15%, in this case, of air, right? Of air content. That's why the air content helps absorb this extra pressure, right? The extra pressure due to the expansion of water in a concrete. Now, what happened is that this kind of freezing thawing issue or thawing problem here, it tells you, this is exactly what we were saying. If the aggregate itself is saturated with water, has no room for the water to expand, it will push against the paste, and that's what we call destructive. It produces something called destructive hydraulic pressure that will develop in a concrete, and this destructive hydraulic pressure will cause separation and induce cracks. And the problem, if these cracks start joining each other, then you talk about accelerated damage to the concrete due to the drop in temperature. That's why in states where the temperature is very low, they specify, the DOT in New York, the DOT in Minnesota, Vermont, Maine, all these states that has a really very cold weather and destructive, in this case, cold weather, they will specify high percentage of air content to absorb this kind of internal pressure. At least it will improve the survivability of the concrete and due to the freezing thawing. Now, what happened is the next ingredient, which is, we said next ingredient is a most expensive, and most expensive because you are actually, because you are investing in the material ingredient of the cement, investing in it by having, put some large, chunk of energy, right? It's energy in this case, because the energy here is the expensive. Raising the temperature of the ingredient to 1500 degrees centigrade or 2700 degrees Fahrenheit is expensive. What about the ingredient of the cement? It's available everywhere. What's the ingredient of the cement itself? You can make it if you want to. If you can raise the temperature to 1500 degrees centigrade or 2700 Fahrenheit, you can do that. It is silica, lime, silica. These are everywhere. The lime, which is the calcareous rocks, basically is made of calcium carbonate, which is the chalk that you see. It's available everywhere. This one is, no one can monopolize in that. You can find calcium carbonate, which is in this case, it is the ingredient for the lime. Silica is, you can go to the beach and you can just collect silica free. If you put, handful of the sand from the beach, nobody's gonna stop you, said you're stealing the beach sand, because it's free. See that it is not expensive ingredient, and you can add clay to the ingredient of the cement. It will contribute for the content of aluminum and iron that needed in the chemical composition of the cement. So that's the energy is stored. The energy is stored and frozen of these ingredient in what we call a chemical equilibrium state. So that's we call this the product clinker. When we heat it up to that high temperature, heat the ingredient of cement to high temperature, we call it clinkers. That means already have frozen chemical equilibrium in that in this ingredient, and this energy will be released upon adding water. This energy will be released when you add water, become fluid-like, semi-solid-like, to 100% rock-like, which is solid, and that is the magic that the concrete is doing. Now, there's some other terminology you probably need to be familiar with. We call it pozzolan cement. Pozzolan cement is not really cement in its own. Pozzolan, pozzolana, pozzolith. Right? We use this terminology, because it refers to the original name came from Bozzoli, within a mountain in Italy called Bozzoli volcanic mountain that used to be erupting dust. So the dust that comes with that volcanic, this volcano is very fine dust, extremely fine dust. I mean, you look at as it behaves like a fluid, and that's why the best name we have for it is pozzolan cement. And we can have artificial pozzolan cement like a fly ash. Makes sense? Like a fly ash, polymer slag. The product when we produce a steel, can be also when you grind it. Even the granite, the granite, if you grind it really, really fine particles, this has become a pozzolan cement in this case, which is useful. Pozzolan cement is not, it's not a cement. It does not have the property of sitting and hardening. Any cement has to have a property of sitting and hardening, but this does not. Add water to the volcanic dust, it's still nothing, no cementing value. Now, what happens when you mix it, mix this pozzolan with other ingredient, it will form calcium hydroxide, and calcium hydroxide has the cementing, it has the sitting and hardening property. That's why it becomes cement. Now, water available everywhere. Now, we need to use water that's not contaminated. That is, applicable to the concrete, useful to the concrete, not harmful to the concrete. A rule of thumb says any water that has a total dissolved solid in a water less than 2,000 parts per million, it is safe to use it without testing it. Now, beyond 2,000 parts per million of water, you need to test it. In some countries, luckily we have plenty of water. In some countries, the water is really scarce. People don't have water to drink, much less to use in the concrete. So that's why they'll be looking for other sources to mix the concrete with, and they will resort to contaminated water. Now, the tap water, usually any tap water has total dissolved solid somewhere between 400 to 1,200. Most likely about 600, 700 total dissolved solid, and it is really safe to use tap water in the mix. Now, air entraining agent, you remember that when we talk about the pressure inside the concrete, the classical solution for this internal pressure in the concrete, this classical solution is basically comes from providing an air bubble in a concrete. How to provide air bubble? Any detergent will do it, but we use industrial detergent, and that industrial detergent produces so many little bubble, and that's why it is recommended for you to use air entraining agent in case if the concrete is subjected to internal pressure. Now, internal pressure like freezing thawing, right? Freezing thawing, which is because of the water expand and increase in volume, it will reduce, it produce pressure. And that's why if you want to absorb the hydraulic pressure due to the freezing of water, then add air entrained agent or air entraining agent. Resisting for the icer and salt, because osmotic pressure, water goes from pure water to salty water, and during this process it will create a pressure. And the experiment that is probably you are very familiar with is that if you remember this experiment, we have in this case, if this is salty water, look what happened. If this is salty water here, and here distilled water, right? Look at distilled water, then the pressure goes through a film here, because from distilled water to salty water, and producing H here, which is the pressure, right? The pressure, which is osmotic pressure, because the water going from clear distilled water to salty water. Also, it improves for sulfate resistance and resistance to alkali silica activity, because alkali silica activity due to the aggregate itself will produce pressure in the concrete. And this pressure in the concrete can be reduced by these kind of air bubbles. So if you look at the concrete here as a concrete mass and you have air bubble everywhere, so the pressure in this case or the crack will be absorbed by this air bubble. It improves workability. You know why? Because you're actually you're adding detergent, you're adding soap. And literally any detergent will do it. Adding soap, of course, when you put soap in your hand, you become slippery, and that's why it become easy to work with. That's why it improves workability. So adding air in the mix would improve workability, reduce in this case the risk for accelerated damage to the concrete due to internal pressure. Now we have admixtures. Admixtures or additive we can add to the concrete. It improves the performance of the concrete. One of the admixtures that we talk about is air entraining. It improves durability in the environment of freezing, thawing, the icing for the salt and sulfur and alkali activity. So it is good. How we use it? We use salt of wood resin, or you can use synthetic detergent. Will do it. Water reducing agent. In this case, if you look about water reducing agent, the reason why we need water reducing agent is you know that the concrete, which is classical, of course, we talk about classical school here, is that the water cement ratio. Here, if you look what happened, this is water cement ratio. If you plot the compared with the strength, water cement ratio. If the more water you add, the less strength you have. So if for you need to use the minimum water you can live with, right? To reduce the water demand, and reducing water demand, you will be actually, if you're going in that direction, when you reduce the water demand like this, you're actually going upward in the strength of the concrete. So some of the examples we can use is basically, you can use linosulfonate, hydroxylate, carboxylic acid, right? And this is an example of the chemicals that we use. Retarders, we need to slow down the setting time. We can use materials like borax, or we can use any kind of materials that will delay the chemical reaction. Accelerator is the vice versa. I need to speed up the chemical reaction, to speed it up, especially in a cold weather. In a cold weather like nowadays, in a cold weather in another state, in the cold weather, if the temperature drops below 50 degrees Fahrenheit, right? If the temperature become, in this case, less than 50 degrees Fahrenheit, then you probably need to think about adding calcium chloride. Calcium chloride, what it does, it accelerates the chemical reaction, because this chemical reaction, is affected by the low temperature. And if the temperature is very low, that chemical reaction may not even start. That's why it's a good idea to do it this way. Now let's go with the star of the admixture. The biggest star, his superstar of the chemical admixtures is superplasticizer. Superplasticizer, what it does, it is water reducer. When we say water reducer, that means it increases strength, and at the same time it improves workability. And at the same time, what it does, it is a retarder, delay the chemical reaction, delay the setting time, expanding the setting time. An example for the superplasticizer that we have is sulfonated melamine for formaldehyde, condensate or sulfonated naphthalene formaldehyde. This is the star. This is the one that you probably need to keep in mind. And that's why superplasticizer improve the strength, and at the same time, especially for the trucks that is going long distance, or if the trucks has got caught in the traffic. So to delay the setting, they keep injecting superplasticizer to keep the concrete or delay the chemical reaction. Now, finely divided mineral, which is very fine materials. We talked already about the pozzolan, pozzolana, pozzolith, right? Any of these finely, which has helped a lot. Like I said, it is not cement usually, but what it is basically, it is fine materials. it improves workability, it improves stability, it improved plasticity, it's improved sulfate resistance, it reduces alkali reactivity. So it's good. It's good for the concrete. That's why the DOT, wherever you are, in this case, will ask to add this kind of finely materials like pozzolan, pozzolana, pozzolane. Miscellaneous, you can add anything else you can to the concrete to improve it. Let's say dam proofing, permeability, grout gas, and all of this. For example, for bonding, you can use rubber. Dam proofing and use soap of calcium or ammonium stearate, and you can use for gas forming. You can use aluminum powder for coloring. You can use any kind of modified colors, which is carbon black or iron oxide. So we can modify the concrete, the product of the concrete at the very end. Now we talk about the fresh concrete. Fresh concrete, the first thing here, once you have the ingredient ready to be mixed, you put them aside, you start mixing them. And the thing that you need to worry about is workability. Workability for the fresh concrete is extremely important property. How easy you can work with the ingredient, how easy you can transport the concrete, how easy to finish the concrete. We call this one workability. The workability is very critical because you need the concrete to flow in the forms, right? To wrap itself around the reinforcing bars, to reach every corner of the form without any problem. Otherwise, you'll have problem with the concrete, with the hardened concrete. That's why workability is very important, very critical. Things that affect the workability is water content. Definitely, if you increase the water here, right? If the water is increased, right, what happened to the workability? It will increase. But what happened to the strength? The strength go down. This is not good, right? This is not good. Air entraining agent, it improves workability because it's soap. It's soap, so it's increasing it. If you increase or the air entraining agent, what happened to workability? It will increase. Definitely, not only it will increase, and also the strength will be improved. The performance of the concrete will improve. Stability will be improved. You see, that's why it is good to have air entraining agent in the concrete according to the classical point of view. Aggregate size, of course, you don't want to have the bigger size in this case compared to the smaller size. The smaller size will have higher surface area. So to coat the surface area, you need more paste. That's why the size is very critical to produce concrete. Now, aggregate properties in unit weight absorption and aggregate cement ratio, all of these will have effect on workability. How we measure workability? Many things. So the best star of measuring workability is the slump. And the rest you can see it everywhere. This is not very common. Next, I would say the Kelly ball penetration test. The slump test is so straightforward to do it, and the way how we measure it is like this. This is a slump test. It is like inverted cone. The diameter of the cone at the bottom is 8 inches and 4 inches at the top, and the height of it is 12 inches. So what you do in this case, you fill it up in 3 layers and tab it with the rod here. Tab it with the rod 25 times. This is very common. So you fill it for the second layer, right, and tap it with the rod 25 times. And you fill it with the third layer and tap it with the rod, right, in this case, 25 times. So at the end, you level the top and then pull the cone upward in 5 seconds. And then this concrete is going to slump, and that will give you a measurement of workability. That's how it looks like. See that? You put first layer, third layer, second layer, third layer, tap it 25 times. See that every time 25 times, right? And then level the top and lift it up. Lift it up nicely and smoothly. And then what happened? You measure how much the concrete slump. This is the slump measurement here. Obviously, if the concrete is fluid, then it's going to slump more, right? If the concrete is rigid, it will be slump less. Make sense? So that's why this distance that the concrete slumps, right, is a measurement of the fluidity, workability of the concrete. Now, this is the true, true slump. You see that? And this is obviously it is not acceptable. And if it becomes so fluid, then the number that you get, if the number is more than 6, 7, 8 inches, then the number become meaningless. To fluid, it's not. So the true slump is somewhere about up to 5-6 inches of slump, and that's what we can use in the design. Now, setting, the time the concrete sits and harden because of the cement itself. What is this? The setting? It's a stiffening. It's a stiffening of the paste because what happened is that the paste is gonna bind the ingredient together. Is it gonna bind the fine aggregate with the coarse aggregate? That's why it is important. Now, sitting here, there is the period for the chemical reaction, or the majority of the chemical reaction, or the most significant chemical reaction of the concrete is, in this case, approximately 45 minutes without any additives. Make sense? With additives or superstition, it will be different. So the concrete will sit and harden in 2 stages, we call it. The initial sitting, that takes about 45 minutes, right, to an hour somewhere with the concrete that has no additive in it. And the final sitting is approximately between 2.5 hours to 3 hours. Do not agitate the concrete after between initial sitting and final sitting. So 45 minutes work with the concrete, form it, transport it, put it in the forms and so on, and create it, vibrate it, do whatever, right? In about maybe half an hour. Leave it alone for another 2.5 hours. Don't touch it, because agitating the concrete in this critical time will break the bonding, which is very delicate, vulnerable bonding. Don't do it. So you need to stop. Heat of hydration. Heat is because you invested so much energy in heat for the concrete, in this case, to produce a cement. Now, when you add water, you get some of the energy back. And that's why when you add water to the cement, the temperature will increase. There will be heat at the end, at the other side of the chemical reaction. So you see that when you add cement with water, you will produce here, some of the product is heat, and that heat here we call it heat of hydration. And the heat of hydration, of course, this is one of the best equation we use in terms of calorie per gram of cement. 130 calorie per gram of cement for C3S, for the main component of the cement, 60 for the C2S, and 200 for C3A. But between these two, they are major chemicals here. Between these two, approximately about 80-85% of the cement. Yeah, bleeding, concrete bleeds. Yeah, bleeding is healthy. Concrete is supposed to bleed. Bleeding means that you have shiny surface on the concrete. If you see shiny surface on the concrete, then the concrete is healthy and bleeding. Now that means this is not reaching yet the final setting. This kind of shiny surface on the concrete, it tells you it is somewhere, the time is between initial setting and final setting. Do not agitate the concrete or work with the concrete as long as you see shiny surface on the concrete itself. Otherwise, you'll be breaking the most vulnerable bonding that the concrete is doing. So here's what happened. You look into this, the bleeding surface here, and you leave the concrete itself, there's some bleeding, like a layer of water and cement. The best layer in the concrete is this kind of layer between of water and cement. What it does in this case, this kind of water, some of it will be evaporated and some water will come back to the surface. This is water mixed with the very, very fine particle of the cement. And if it dried out, then it will form the best protective layer to the concrete. So do not remix it, do not agitate it, do not disturb this bleeding layer. So what you want to do is this. Now you need to examine this kind of layer. The best scenario you can have, if the amount of water going in, the same amount of water you are losing due to vibration, maintaining this kind of thickness of layer until the end of the final setting. Until the end of the final setting, then the concrete gain enough strength, they can work on the concrete after that. So whenever the bleeding here equal to, the bleeding water equal to evaporation that comes due to the the heat, the temperature, and depends where you are, then if they are equal, you're creating a perfect layer, perfect strong layer in this case. This is perfect strong layer on a concrete, protective layer on a concrete. Now, let's talk about mixing and proportioning of the concrete. Here's what we do, mixing it. Now you have the ingredient. Now let's work on what mixing it. The thing that you need to go back again and remember, what is concrete? You know, just what is a concrete? Concrete is composite material. Composite means because we say this word because we are making the concrete of different ingredient. We make it from the cement, different than aggregate, and aggregate can be anything. Sand and gravel can be anything. That's why it's composite. Composite material composed of the cement or the binder itself, called the best binder that we have nowadays, and you can find it in stores, the hardware stores, is Portland cement, the star of the cement. And this is the binder, and the rest is the ingredients, which is sand and gravel and water. So this is just to remind us that is when these are the ingredients how I make the concrete. Now hydration is a chemical action that's triggered by adding water. When you add water, the chemical action starts, and then bonding starts, and binding and bonding starts between the ingredients of the concrete. So the chemical action will be triggered by adding water, and then convert all of these kind of ingredients, loose ingredient, into a solid rock, solid man-made rock, bonding all the ingredient together. So this is the hydration process. A lot of people, so that's why it's a simple process. Simple process, just anybody can do it. Just add water at room temperature, done. But yet it is very, very complicated chemical action. It's not simple chemical action, but it is simple process. Now, what we do in a mixing, you design the mix. You design the mix to produce the best product at the very end. And the best product at the very end will give you, the good strength, good durability, right? And you design the mix, design the proportioning of the ingredients, how much you need of the cement, how much you need of the sand, how much you need in gravel, how much you need to add water, and you mix them all together. The reason why you target the best mix design in order to come up with the best outcome or best result, which is mostly you'll be targeting higher strength. You need strength because concrete, you make concrete, you build bridges out of concrete, you build building to take care of the loads on these kind of structures. You need higher strength. You need good workability. You need also the cost to be, reasonable, to minimize the cost, because you are in competition, and nowadays the competition is all over. The whole world is competing with you. That's why, in the past 25 years, there's not much communication between the world. Now we have good networking, good communication. That makes the competition is very high. You demand to look into reducing costs and make it more effective is very high. Now to say, well, what is to reduce the cost? Here it is, to reduce the cost is, in this case, work on the most expensive ingredient, which is the cement. The cement is the most expensive ingredient, so reduce the amount of cement by, at the same time, do not increase the strength, do not jeopardize the strength, reduce the cement without jeopardizing the strength, reduce the cement without jeopardizing workability, by playing, in this case, tricks on the ingredients, by mixing or designing the mix in most efficient way. You get good strength, good workability with the least cost possible. So we minimize the amount of cement, you have good gradation, because one of the tricky part here to improve the strength, the cheapest way possible, is to work on the gradation of the aggregate itself. And that will give you the best kind of gradation. Now, at the same time, you need to look at the water cement ratio. We already said that the water cement ratio look like this. For the strength compared to the strength, this is the water cement ratio. This FC prime is the compressive strength of the concrete. Work on the water cement ratio to improve the strength of the concrete and improve plasticity. Now, increasing water cement ratio will increase the plasticity and fluidity, but reducing the strength. So increase water cement ratio, reduce and decrease the strength due to larger voids. Not only larger voids, it also due to have too much excessive water in the concrete, and any excessive water left in the concrete does nothing but damage and damage and damage to the concrete. Remember that. Here's a secret. In normal circumstances, right? Usually we use, for the hydration process, you need approximately water cement ratio 0.23. Okay, that's the water cement ratio. But in reality, we cannot even mix it because it looks too dry. Imagine you put drops of water on the mix, it doesn't mix. So we become reluctant to use approximately about 0.5. So in other words, this is typically to use 0.5 as a water cement ratio. So what actually we're doing, we're actually using twice as much water as needed for the hydration process, because you can't mix it. It doesn't mix. Imagine it will be very dry. It doesn't mix. So what happened is that half of the water we are adding in the concrete will go for the hydration process, right? And the other half, we call it excess water. Excess water, what it is basically, this excess water, it does nothing in the concrete but damage. The only thing it does, damage. It has no role in the concrete but damage. If it freezes, it's gonna create cracks and pressure inside. If it evaporates, it's gonna shrink. The concrete is gonna shrink. Makes sense? And not only that, it leaves voids in the concrete that will reduce the strength. So that's why the tricky part is that how can we reduce the excess water? How we reduce the excess water to improve the strength of the concrete? This is the tricky part. Keep that question in mind. I'm trying to reduce the excess water, reducing excess water, reducing the shrinkage and shrinkage cracks, increasing the strength, right? And at the same time, reducing the void in a concrete. So in the design of a concrete, you have major principle that you have to worry about, which is basically you are looking at quality. You need quality concrete, because when you mix it, you target the quality of the concrete. Get me the best mix that could give you that can get good quality, good workability, and low cost. So these are the major target when you start designing the mix, proportioning the ingredient. Keep in your mind, these are the three things that you have to have. Now we talk about, once you mix it, we're going to be talking about the hardened concrete. Now, hardened concrete, now the concrete sits on hardened now. What you want to do is the following. In hardened concrete, you need to, look at the properties of the hardened concrete. The major property of the hardened concrete is the strength. You need a stronger concrete, so we need to test the concrete in terms of the strength. All kind of strength: compressive strength, shear strength, tensile strength, flexural strength. You are after to make sure that the concrete, you get the final outcome the final product is strong enough to take care of the loads on the concrete. Elasticity, water tightness, resistant destructive agency, volume changes, the creep, extensibility, all of these are properties important for us whenever we deal with the hardened concrete. Okay. Now, when it comes to strength, here, concrete strength is basically the compressive strength is number one, and probably the only one we are, obliged to do. The only one that is required by the code is the compressive strength. Compressive strength, we call it FC prime. FC prime, what it is basically is the load, the maximum load a cylinder can take over the area. Makes sense? So what happened is that we take cylinders. Normally we take cylinders, in this case, 12 inches high and 6 inches, right? This is the standard cylinder that we have. It's about 12 inches in height and 6 inches in diameter. Now, what happened is that we start using, this is 6 by 12, but most of DOTs now, they use 4 by 8. Then take this cylinder, put it in a machine, and apply load on the cylinder. It's gonna break most likely by shear. And this is the maximum load here it can take. And if you take the area here, cross-section area, then if that's the case, then FC prime, which is the compressive strength, will be this maximum load over the area. Now, the tensile strength is also needed. Tensile strength, splitting strength, all of these are expressed as a function of FC prime. Make sense? So once you know FC prime, you can tell about the tensile strength, splitting strength, and other kind of strength. Now, what happened is that the compressive strength, like we said, if you put the sample in a machine, there's 3 typical mode of failures of the machine. One of them is that failure due to cohesion, like tensile strength, tensile stresses, or shear or compression. The way how it works, how it breaks. So in a tension, if you put the sample in a machine, so the failure will be like a load like this way. For the shear, the failure will be looking like this, usually, like a cone, like this. And for, compression, of course, crushing. Now, you probably need also to look into the stress-strain relationship of the concrete. Basically, about 45% of the FC prime is linear, and after that, it becomes non-linear. According to this is epsilon naught, give you the maximum stresses can get, we call it FC prime. And it failed, in this case, FC prime, it failed at some certain, strain, but according to ACI, this epsilon naught is approximately 0.002. And this is ultimate strength or strain in this case, which is 0.003. What happened is, according to ACI, the concrete fails when the strain reaches 0.003. So according to ACI here, there's nothing, we drop the strength beyond this strain. Obviously, for a concrete cylinder look like this. Now, the strength of a concrete increases with time. In the first 7 days, approximately 70% of the 28 days strength. In another 7 more days, you only gain 19%. And you can tell in this case, the gain of the concrete strength with time slows down. The rate of gaining strength slow down. And of course, the 28 days, we call this is where we can use it. And that's why it is good idea for us, to be aware how the concrete gains strength. So the first 7 days is the most critical 7 days. That's why we are required to cure the concrete for the first 7 days. That's the most bulk or the biggest bulk of the gain of the strength of the concrete with time. Now, as look what happened. From 6 months to 1 year is only gain 4.04% or 4%, right? So we can tell it is the rate of increase in strength reduces with time substantially. But theoretically, we can say that the concrete gains strength forever. That's how it looked like. You see that? It gains strength very, very sharp at the very end. Then the rate of increase, in this case, what happened to it, decreases, and then almost like a flat, but theoretically, the gain in concrete strength will be, will be infinite. The concrete will gain strength infinite as long as it's not subjected to harmful chemicals or harsh kind of condition. Now, again, we express the tension in this case, on the tension, the shear, all this we express them in terms of the compressive strength. And as a rule of thumb here, that the compressive strength of the concrete in this case, and compared to the tensile strength of the concrete, rule of thumb, tensile strength is 10% of the compressive strength. See how weak the concrete is when it comes to tension? Concrete is extremely very weak when it comes to tension. Extremely weak, very, very low percentage in this case, according to the formulas that you can find in codes and other kind of literature. The tensile strength expressed in this case, the tensile strength is 5 square root of C prime. This is one of the best formula to relate the tension strength or tensile strength with the compressive strength. Notice that FC prime will be in terms of PSI. Now, when it comes to the flexural strength, what we do is that the flexural strength is like we use it in a beam, and a beam in this case, what happened if you have a simply supported beam look like this, and you load it, what happened to it is that it's going to be the top will be subjected to compression, and the bottom will be subjected to tension. So that will be indirect way. This is the Newton axis here. So indirect way of measuring the strength of the concrete. This is the concrete in compression. This is the concrete in tension. Now, once the concrete, in this case, once the concrete beam breaks, see that? It's subjected to this kind of loading. Once subjected with one load or two loads, then it's gonna crack here. That means that it reaches, it's cracked by the tension, and this is tension here that caused the crack or failure. We call it modulus of rupture. Modulus of rupture. So modulus of rupture is tensile, indirect measurement of tensile strength of the concrete in flexure. Approximately maybe 11 to 23% of the compressive strength, it goes for the flexural strength of the concrete. So the setup according to ACI, the flexural strength of the concrete is approximately 7.5 square root FC prime. And the setup of the experiment is how we do that. We apply load P. Obviously, this will be P over 2 in both here, the load, and this will be P over 2. Now, if you start doing some derivation, the tensile strength will be MC over I, and C for the concrete will be equal to H over 2, and I in this case moment of inertia will be equal to 1/2 of the width, or 1/12 the width, BH3. If you put this all together, you end up with the modulus of rupture FR equal to 6 multiplied by the moment. And the maximum moment here for this scenario would be equal to PA/2. A, PA/2. A is this distance here. Okay. Now, there's another indirect way of measuring the tensile strength, which is you put the cylinder on the side and apply a linear load. According to Timoshenko, this will be failing by the Poisson's effect. Poisson's effect, in this case, you have the cylinder here, exactly like you have, the watermelon. If you push on a compressive force and the watermelon goes for tension. So the part of it will be compression here, but the most of it will be in tension. So that's why the cylinder will break in very nice, kind of almost in the middle, and split. That's why we call it splitting strength. According to Timoshenko derivation, the splitting strength here is 2p/pi/LD for a standard 6 inches by 12 inches, right? Cylinder. Then the length is 6 inches, length 12 inches, and the diameter is 12 inches. Now, according to the studies and research, this is the splitting strength of the concrete is expressed in terms of Fc prime, which is approximately 5 to 7 square root of Fc prime. Most likely will be equal to 6.7 square root of Fc prime. And notice that Fc prime is expressed in terms of PSI. All right. Shear strength is another strength that we target when two planes parallel and equal. One of them is has tendency to slide, and that will cause a shear in the concrete. Shrinkage and creep. Of course, one of the major problem of the concrete, it shrinks because it loses moisture, and losing the moisture, of course, will leave void, and that's why it shrinks. Shrinkage, they are due to water loss to atmosphere, and plastic shrinkage occurs when the concrete is still wet. Some of the water is used for the hydration process. A drying shrinkage is the one that occurs after the concrete has set, after the 3 hours, right? Where the excess water is leaving. Remember that? We talk about excess water is leaving the concrete. That's why excess water, right? The water, that's the one. When the excess water leaving, and most of the shrinkage will be approximately in the first few months, about 80% in 1 year. The cycle of shrinkage swelling, it depends on the moisture content of that in the concrete. Okay. Now, concrete property, shrinkage, in this case, you want to reduce the shrinkage as much as you can, because the shrinkage is not a good property that you have, because shrinkage is one of the major kind of generation or production of cracks. So it is not healthy. It's not healthy to have a concrete that has high percentage of shrinkage. It's not healthy. So you want to reduce shrinkage as much as you can. To reduce the shrinkage, you need to reduce the water cement ratio. To reduce shrinkage, what you want to do is reduce water. To reduce shrinkage, you need to use aggregate and content, which is modulus of acidity. In this case, has least kind of absorption. Reduce shrinkage, of course, you need to talk about something we call volume to surface ratio, and that will reduce the amount of shrinkage. So the shrinkage is not something that we can tolerate very often, because this is one major source of crack generation. It generates cracks that's unsightly and somehow causing defect in the concrete. Now, also shrinkage is a function of the type of cement that we use. Sometimes we don't question what type of the concrete, the cement itself, if it is certified as Portland cement type 1, we sometimes don't question it, but it is a shrinkage has something to do with the type of this of the cement, because this part of the hydration process is to take the water, is absorb the water or use the water in a chemical reaction, and that's why the cement is it has a major factor in the shrinkage. The admixture that we use has a major factor, especially if you use superplasticizer. Superplasticizer, what it does, it reduces superplasticizer, it reduces the water demand. And of course, if you reduce water demand, that means you reduce the amount of water, that means it will reduce the shrinkage. And of course, you know, typically the shrinkage or strain due to the shrinkage is between 200 to 600 micro strain. So that's why it is a big amount. Now, when it comes to shrinkage, sometimes we have drying shrinkage for slabs and concrete. The top surface will dry faster, and if it dries faster, then the top will be curving upwards. So it look like, of course, if it is like slab on a grade, so what happened is that it lose contact with the ground, and that's why when it's subjected the tip of it to the load, it will reduce a crack in this side. So that's why this is, we call it in this case moisture gradient. Moisture gradient is very similar to temperature gradient. Temperature gradient in the nighttime, what happened in nighttime, the bottom will be at higher temperature, right? In this case, the temperature T at the bottom here will be higher than T at the top, right? If the the temperature at the bottom higher than the temperature at the top, then it behaves like this. And I mean, if the other way, if the temperature at the top is higher than the temperature at the bottom, then it will go, then the slab will curve this way. Concave upward and concave downward. It depends on the moisture gradient and temperature gradient. Now, this is the typical shrinkage. It loses moisture. And sometimes what happens, if you restrain the shrinkage, that will create cracks and unsightly cracks. That's why we need to control where the cracks are going to initiate. So the best way to do it is that do not restrain movement of the concrete beams or concrete slabs. Here's another, you can tell that restrained shrinkage, if you see parallel cracking approximately maybe 8 to 10 feet apart, then what you're going to have, that means you are not providing, if it is restrained, that means you are not providing the concrete the freedom to move. And if you restrain it, then you're going to start creating cracks approximately here with a parallel crack with approximately 8 feet apart. So that's why when we cast slab on a grade, we put plastic sheets on top of the gravel. And these plastic sheets on top of the gravel will minimize the contact and the bonding with the aggregate. Now let's talk about defect of the concrete. Concrete major defect with the cracking. Concrete cracks, whether it's due to the load or whether it is due to losing moisture, due to the shrinkage, and so on. Now, one of the things that we need to worry about is reduce the amount of cracks, and to do that is that we have to design the mix properly, design the concrete members properly, but the cracks result in many different ways. And one of the major crack generating kind of measures we have, if you restrain concrete, then it will generate cracks. So that means if you restrain the movement of the concrete, and then the concrete shrinks, right? And if the concrete shrinks, it's gonna cause the cracks if it is restrained, right? Of course, we have thermal contraction due to poor practice. And sometimes thermal contraction is another way to do it, right? If you have too much more water in the concrete, then the drying shrinkage become one of the major cracks in the concrete. If it is restrained, if the concrete has nowhere to move. Now, there's another kind of, if you don't, because of thermal expansion and contraction, you have to worry about these things. In other words, one of the things that probably it is very easy for you to look at it, in case if you have, let's say you're casting a slab look like this. Notice that if you do not make here some kind of construction joint, then the concrete will crack this way. Makes sense? That will be unsightly. Now, if you have a column in the center here, and you do not have here also a joint, then the concrete will in this case will crack around it, because the concrete bond to the column. Of course, if it is here with the wall here, for example, if you do not make a separation here or isolated joint or isolation here, because you have to make isolation at the column, isolation here, then if that's the case, they will cause, because the concrete will bond and will cause a crack at the side. So construction joint, are too far apart. Sometimes what happens when you have slabs, you have to make approximately 20-25 feet apart. If not, then the concrete will create its own kind of crack. Contraction joints are not deep enough. Sometimes what happens is in a concrete slabs, we don't cut the slab all the way to the bottom. We cut it on approximately 1/4 of the depth. If this is H, we cut it H/4, right? And that will eventually is gonna crack like this. And so at the top, you see it clean, nice kind of cut, and that's why how we control the cracks in this case. The slabs are strongly constrained to the parameters. That's what we talk about here, and we have no isolated joints around the column. That's what we talk about here, and low strength and deficiency. Other kind of cracks that's generated in the concrete could be due to uneven support by poorly prepared subgrade, and this is very common in structures. If you have foundation that look like this, see that foundation look like this between two columns. I'm trying to draw it here. Obviously, they have doors and windows. See that? So what happened is that support settlement somewhere here. If this here in this case, this is settled, then it's gonna create a crack in that direction around the corner, right? Expansive clay, there's also a force that can uplift and bring down the structure. We have sulfate resistance, improper jointing, and impact, and all of these are can cause some cracking. So the other kind of defects we have, we call it mafic cracking. Mafic cracking is about maybe 3 millimeter deep. It's not really major. This is really unsightly, the only thing, and you can see it whenever the concrete is wet. It looks like in random. So causing of it because you have a poor or inadequate curing, or too wet mix, or finish while the bleeding surface, the shiny surface is on still there. Or some people, what they do, which is very, very, very unhealthy kind of practice, they sprinkle cement, right? They put a new cement on the top of that, they sprinkle cement and put some water, and in order to mix it up, make it easy. This is big no here that will create a problem. And carbonation whenever the concrete, in this case is fresh. If the carbon dioxide or carbon monoxide is mixed with the water, that will cause carbonic acid and will cause this kind of mapping. To crazing, there's also another kind of defects we call the crazing, and what it is usually You reduce the effect of it by, do not sprinkle or trouble water, do not sprinkle cement, or do not perform finishing, in this case, before the bleeding water is dried out. Do not overwork, do not allow the curing in this case to be interrupted, and allow wetting and drying stage. So these are the things that you probably need to worry about. Dusting, causes of dusting. If you rub your finger or thumb against the concrete, if you feel the finger is full with dust, this is because, because of dusting in this case, there's some fine particles that's not bonded in the concrete because of overly wet mix at the very top, or the floating, traveling, while you're bleeding surface. What happened? You remember we talked about the bleeding surface here, this bleeding surface at the top here. If you start disturbing it, then you end up with dust at the top. You use a lot of dirt or clay. Yes, I agree. I agree with you, Jared. I added a few slides at the last few moments. And if you like, we can email you the new one. Thank you for this note. That's true. If you, Jared, he just has you sent me a chat message that he said, well, this slide is not there. Yeah, I agree with you. Because I just added them last moment. I thought this is probably, you find them useful for you to look at. And again, we'll make sure that you provide with the latest. Okay, is that okay, Jared? Right, thank you, Jared. So the way how to repair the dusting is, because the top surface would be loose. The way how to do that is remove the loose materials and use some kind of epoxy and material that's bind all these kind of materials together. And in severe cases, what you do, you put additional layer on the concrete. Scaling is a scorpious condition of some surface after exposure to the freezing thawing problem. Basically, you can see circles of chips, right? That's somehow exposing the aggregate itself due to the freezing thawing inside the concrete. It is usually a very thin layer of the concrete chipping off. You can see it if you look down on the walkway. You can see a lot of it, a lot of these in this case. Scaling, the cause of that, because you're using non-air entraining agent, because the air entraining agent absorb this kind of pressure, water pressure in the concrete, because you of excessive amount of calcium or sodium chloride, because of any finishing, while the bleeding water is still on the surface, because insufficient curing and inadequate thermal protection. These are what causing the scaling. To repair it, of course, what you're going to do is to clean the surface and apply a bonding layer, which it could be use Portland cement or use latex modified concrete resurfacing or polymer modified cementitious material to repair it. Now, pop out, it is not really quite unhealthy, but it is unsightly because of internal pressure. What happened is that there will be aggregate here. The main cause of it is alkali aggregate. This alkali aggregate, because of this activity, what it does, it will cause some kind of internal pressure, especially whether we have aggregate here or whether you have reinforcing bars too close to the surface. That the concrete cover, if it is too, very thin, then that because of the movement of the steel reinforcing bars contracting and expanding, this will cause some kind of pop out. So this pressure is due to expansion or chemical change, either due to the aggregate itself or the expansion and contraction of reinforcing bar in a concrete. Now, usually about between half an inch to 2 inches, usually they do not really diminish the value or the concrete strength, but usually unsightly. And there's other kind of causing of to protect it from pop out, use non-offending source of aggregate, because the aggregate is the one that has the chemical reaction we call alkali reaction. You could use two courses of construction, right, using selected of imported aggregate, and prohibiting application of impervious layer, right, and use low slump. When low slump means high strength, a strength of concrete that is really have good resistance for pumping. Blistering is exactly like we have blistering in the skin. Basically, there's the layer here at the very top is this dense layer. You're creating a dense layer, which is basically the one that's bleeding water. Remember that? Dense layer, and then the water is going to go, will somehow evaporate and reach to the surface. It has no room to go, so it would be trapped here, applying pressure trapped, causing this kind of concave the surface. We call this one blistering. The causes of that is very obvious. When sometimes what happens, you have a sticky kind of mix at the top surface because due to the excessive entrained air, or excessive fine, the very fine particles. The fine particles fill up all the gas mix, the top surface completely impervious. Well, some people, what they do, they are overworking with the jitterbug or the finishing. So overworking with the top surface, in the finishing, that will make it very dense. So these are the things that may cause it. Now, spalling is a serious problem. Spalling, this is big chunk of concrete will be detached of the, it will be somehow breaks off, exposing the reinforcing bars. Once you expose the reinforcing bars become vulnerable. The reason why we like to put layer of the concrete around the reinforcing bars, even though this layer may not be needed for strength, it needed only to cover the reinforcing bar, to protect the reinforcing bars from corrosion. And if that's the case, then we do need to, and to protect the steel reinforcing. If it's not protected, then the steel reinforcing bars will be corroded. And the reason for that, insufficient depth of the concrete cover, inferior kind of mortar and concrete, and poor bonding. And that's why poor bonding may cause this kind of problem. For the basement, there's a lot of cracks in the basement, either due to the drying shrinkage or settlement of the supports, or sometimes structural cracks due to the backfill behind the basement wall, or sometimes most of the cracks you can find in basement due to improper joint. You do not have construction joint. This is typically how we can see the cracks in the basement. What is basically, notice that at each opening here, at the corner opening, there will be some cracks, and there's a cracks because there's not enough. In this case, about 20, they are more or less about 20-25 feet apart. They don't have proper construction joint, and sometimes you have to horizontally crack due to the pressure from the soil in the back of the basement. To fix it, in this case, you have to use uniform support. You have to use concrete. You have to be placed at moderate slump. That means you have high strength concrete. You have to have proper construction practice, and to improve the concrete, to improve the performance of the concrete, to improve the the drop height and the formwork and waterproofing, and control the construction joints somewhere between 20 to 30 feet. Backfill should be carefully done by design, and so on. If you follow all of these kind of rules for the basement, then you'll produce, then you'll have a good basement. So this is another thing that here we haven't added, like you were asked here. It's also added a slide to tell you about the chemical, some kind of material that's harmful to the concrete. One of it is carbon dioxide. Carbon dioxide is a gas. It's harmless to the concrete. Once it dissolves with what becomes carbonic acid, what it does, it dissolves the concrete is slowly. The way to protect concrete is to provide some surface, some protection or protective coating. Carbonic acid, we already talked about. Garbage has all kind of chemicals that is harmful to the concrete. What it causes to it is disintegration of the concrete slowly. To protect it, also you need to put some kind of coating to the concrete. Some gasoline is not really harmful to the concrete whatsoever. So if you spill gasoline in concrete, hardened concrete, it shouldn't have any effect. Lactic acid, it slowly disintegrates, which comes from milk, because acid slowly disintegrates concrete. So the best way to do it is to protect the concrete by having some coating, plastic coating or epoxy. Milk, as a fresh milk, has absolutely no effect on a concrete, but when it becomes decayed, it becomes sour, and the sour is lactic acid. And another kind of problem that we might have is nitric acid. Again, nitric acid is a solution. If it's a strong solution, will cause disintegration of the concrete. You can use protective coating. Seawater to the plain concrete has no effect. But whenever you talk about, in this case, reinforced concrete, because seawater has a high content of salt, it's causing some corrosion to the reinforcing bars. And to protect these reinforcing bars better, if it's subjected to the seawater, you need to increase the concrete cover. You need to increase the concrete cover between, let's say, 3 inches to 5 inches or 7 inches. Vinegar acid, of course, it does the same thing like any kind of acidic materials. Sewage, it has mostly all kind of, harmful kind of chemicals, including the most dangerous one is sulfuric acid. Sulfuric acid, it causes some disintegration of the concrete. To protect it, you have to isolate the concrete from this sulfuric acid by using some bituminous asphalt layer or epoxy. Sugar, if it is dry, has no effect on the concrete, but whenever it is in solution, it may become an acidic material. Now let's talk about the concrete in the past, the present, and the future. Just show you a few pictures here to make you feel that the concrete is that majestic material. That's exactly that majestic material that is, we've been doing it. It's a pride of nation. Whenever any nations, they said they build the biggest dam in the world, the tallest building in the world, the longest bridge. This is a pride of a nation. That's why concrete is in the heart of this. This is here very old. Look at the bridge on the top left. It is built in 1897, and still very proud. That whole nation is a proud of that. And there's another bridge, you can see it here, which is in Oregon. Look at how pretty that is. It built in 1914. It's about 14 meters span. There's something just so cute with these kind of majestic pictures for you to have a better appreciation of that concrete material. This was 1997, a bridge that is being built, crossing the river. So look how pretty that is. And there's also in Canada, there's another bridge that's really very, very spanning, stretching all over. And this is done by, the slip forming technique, technology. Now look at here, look at the concrete that's been built, this one in Sweden and in Denmark, the bridge that's connecting in between Sweden and Denmark in 1998. Look how proud these people when they build it. Look how majestic that is. That makes you appreciate the concrete. In France, there's another in 2004. This nice, good-looking kind of bridge. You see that, like somebody suspended the bridge. How about that? I mean, this is also something that makes people proud of, belong to this nation that's able to create and build these mega structures. There's also here in 2009, let's look at that nice, good-looking bridge. It is really majestic. So that's why it is good idea for us to look at the concrete now as a future material. Now, concrete can be also composite kind of materials. You can mix it with the steel. You can mix it with other kind of materials to make the concrete, or the performance or design the members. Now let's talk about the concrete. The concrete as a materials. Now the new technology, the new materials, the new majestic materials, the man-made rock by adding water. Just add water. That's it. Have the ingredient, add water, mix it up, and wait for not too long, 2-3 hours. You're creating rock, a solid rock at room temperature, no machinery, nothing you need. You can mix it by your hand. There is earthy kind of ingredients, which is between cement and aggregate, it become rock. And concrete is the second most consumed materials on earth after water. Think about this. Think about this kind of majestic material. Think about that. I mean, show me any other material, any other materials. Right? Plastic, you need pressure. Steel, you need, temperature in thousands of degrees Fahrenheit, right, to produce it. But this is nothing. It's just kind of put all these ingredients anywhere, Anywhere, anytime, any temperature, you can produce a rock, and you can build on this rock giant structures. And not only that, this material is very common materials. I mean, we consume more water than concrete. That's the only thing, and the rest is concrete. Normally, the estimate is that we currently manufacture about 1.7 billion tons per year, approximately 4,000 cubic miles per year. Each person on this planet will have his own share, but 1.3 cubic yard per person per year. Think about how much we produce out of this material. And not only that, I mean, we're not stopping. We're going to be producing more and more because the prosperity, progress, the rise of a nation comes on the top of concrete foundations. You must understand that. And look at the war in Ukraine. They are targeting civil concrete structures because this is the foundation of civilization. You can bring a nation from developed, completely, advanced nation to nothing, to even into the Middle Ages by just destroying the civilized symbols, which is the concrete-made structures, bridges, dams, buildings, and this what makes the civilization. In the future, we are anticipating to actually use twice as much, 3 times as much, but maybe 3.5 to 5 billion tons a year in 2050. So unfortunately, whenever we produce cement, we produce carbon dioxide. We are the one of the major carbon dioxide producer, because every ton of cement about 1,700 pound carbon dioxide, but we cannot help it. Well, this is because the advantage of concrete is way over the amount of producing the carbon dioxide. We contribute 5% of the total carbon dioxide that emitted in the whole earth. And now MIT did a research lately, and they publish it. This is published information to reduce amount of carbon dioxide in the process of making cement. Unfortunately, the best they could do is to reduce it by 11%. Well, I mean, that's just for you to know. That is, we produce it. Now, so what's the concrete? Concrete is simple materials, but it's still very complicated kind of material itself. Simple, complicated. John Doe, who doesn't know, can make it, and professors can make it. Just look at it differently. Just look at it quite differently. So what does it tell you? It tells you concrete is a simple but yet complicated. It is a social and cultural statement. When you build, let's say, the Opera House in Australia, the only people remember the Opera House, but they forget it's Australia. It's a symbol of nations. The Eiffel Tower maybe is more famous than France itself. And Hoover Dam is more famous than any state that the Hoover Dam served. Am I right? So look how famous these structures become. It has a name. It has a name. Even we call it with he or she, like the Hoover Dam. Look at that. The tallest building has a name. The tallest bridge has a name. It becomes like a symbol of a pride, cultural statement, social statement. It is a stretching of muscles for the other people who think that they can be our enemy. I mean, I can intimidate my enemy by showing how strong I can be by producing, building mega structures. So it is, what's a concrete again? It's a classical material, contemporary material. It is everything. The materials of many kind of contradiction. It's a strong material, but weak materials. Very strong in compression, very weak in tension, and all of these kind of things. So understanding it's not that simple. That's why people sometimes they say concrete has a mind of its own. It doesn't have a mind of its own. You need to understand it. It is, you just kind of, you do not have the desire and will to understand it. Of course, the concrete behave different than what you expect. So concrete can be in any kind of form. So steel, we produce steel, but it's produced in different kind of shapes, like beams and columns, and build it like a Lego. But in the concrete, I can shape the structure the way I want it. I can form it the way how I want it and build it. So on site. Now, here's something you need to remember. In 20th century, the focus was basically on the chemistry of the cement. Once we discovered the Portland cement, we said, stop, don't do anything. No one is allowed to change it. We reached the ultimate kind of magical material, which is Portland cement. And we were not allowed to challenge it. We were not allowed to improve it. We thought that we reached the maximum. Nothing better than Portland cement. And we exhausted the talents of engineers like you and I, not to come up with better Portland cement or improve the Portland cement, but we exhausted and dedicated the talents of engineers toward codification and standardization of this Portland cement. And if you want to improve it, don't improve the Portland cement, come up with a new material to adjust it. That's the biggest mistake. This is the biggest mistake that's been done and make us lose, in this case, at least 50 years of advancing the concrete. You need to remember, this is the biggest mistake that we've done, especially Portland Cement Association. They are guilty of depriving us of improving on the concrete. And here's it. 1980s, we realized that the problem with the strength, limit on the strength of concrete comes down to the void in the concrete itself, and this void because of the excess water. And if we have it very well compacted form, right, then you end up with good concrete. So we start trying to come up with a new mix, and we reach the point that yes, if we really compacted the concrete materials in a dense form, then we can reach a very high strength concrete as strong as a steel when it comes to compression. And we call the material high strength concrete. Then we call it high performance concrete, which is increase the stiffness, workability, and strength. Now here's what happened in 1990s. I'm not sure if you're a young engineer, probably this is way too far, but for me it is like yesterday. We produced concrete, we call it ultra high performance concrete. Ultra high performance concrete is basically trying to reduce the void to the zero in a concrete. And we realize in this case, the problem that somehow is blocking us from getting to the strength of concrete in tens of KSI. Okay? So we start looking into improving changing the Portland cement. We want to change the Portland cement. The problem is the Portland cement, and we cannot use Portland cement to go that far. Portland cement was a stumbling block in the progress of a new concrete. So we pushed the Portland cement aside, and we produce a new cement. And this new cement is produced by a German and French company, Ductel and Lafarge, a chemical engineering company. And this is the new magic in this case. The new magic is that Portland cement is no longer the one that's the best to have, and this is the new materials. And the focus now is on the structure of that new materials. So to sum this up, the trend in 1980s was in sub-millimeter, in 90s was nanometers, and then we're going to be working to smaller and smaller scales. So for millimeter to micrometer to nanometers in 1990s, you can tell nowadays we're looking at atomic scale structure of the concrete, and we're producing concrete with extremely very high strength. So what's the secret? The secret is calcium silica hydrate. This is calcium silica hydrate, CaOH2. See that? This is the one that is produced, that's produced when you add water. What it is, the secret, you remember when we talk about the water cement ratio for the water cement ratio, for the hydration process we needed for hydration is 0.23, and we actually use 0.5. But this is the new material. We use water cement ratio equal to 0.11. Now we might say, well, I need hydration for hydration 0.23. This is what the secret is. The secret is that you hydrate half of the cement, which is not Portland cement, half of the newly produced cement, and then this half that's hydrated will combine with the calcium silicon hydrate and continue the chemical reaction. As simple as that. Make sense? So what does it mean? It means zero excess water. What does it mean? Zero porosity in the concrete. What does it mean? Zero void in the concrete. Make sense? Or approximately zero void. So you hydrate half of the cement, and that half will combine with calcium silica hydrate, and that's where the chemical reaction continues. So it appears that calcium silicate hydrate manifests itself into two different forms, low and high density. Now high density gives you higher strength. This is the whole thing that is behind the new invention of the new cement. Now this is high performance. In this case, we use we call the materials ultra high performance fiber reinforced concrete, which is uses special kind of cement. It's not the cement that we use. And we use even fine materials, approximately 600 micrometer to 0.1 micrometer. We use water cement ratio 0.11, very small. That means there's no excess water for sure. And sometimes you use fiber and metal fiber to increase the strength here again, and organic fiber for fire to protect the concrete if the concrete is subject to fire. Now, admixtures, we can use admixture later on. So that's the whole secret. Now, for the ultra high performance fiber reinforced concrete, the fibers, it be steel fibers with the diameter 0.2 and a length approximately half an inch. By a volume, not too much, about 2% by volume. Now, not only that, we have organic fiber or press-resistant. In this case, organic fiber, the main purpose of the organic fiber is to improve ductility without reducing the strength. Give some ductility, because it's let it deflect. The press stands for ultra high performance fiber reinforced concrete, suitable for the press, because we do need, the limit was on press concrete was the strength of the concrete itself. Now we have high strength concrete that open doors for the press concrete. So the ultra high performance fiber reinforced concrete is proven to be an excellent material, resist for high temperature due to the organic fiber. Organic fiber in the concrete, it will evaporate, leaving some space in the concrete to absorb the steam that comes out of the fire that we have in the buildings or structures. Make sense? So that's why the main purpose of the organic fiber to absorb the steam that comes from the fire. So the microstructure of the ultra high fiber is completely closed. So that means you do not need to use air content. You do not need the water to go through it. It's completely closed. Water does not penetrate into it. If it doesn't penetrate the water into it, then that means no freezing thawing problem. There's no excess water. There's no shrinkage. You think about that. This helps improve the chemical stability and the materials and resist any kind of chemical attack on the concrete. At the same time, reducing substantially the freezing thawing problem. So think about that. This is something that we have to think about it. Now, a compressive strength reaches 26 KSI. How much the allowable strength for A36 steel is 22 KSI. This is for steel. Look at that. We exceeded the A36 steel allowable strength. The tensile strength 1.2 KSI. The flexion of 5.8 KSI. And not only that, the most important property that I like, it does not shrink. If it does not shrink, that means there's no cracks. Unlike the traditional concrete, unlike the concrete that's made of Portland cement. Now we can say, what happened? These people wasted 50 years, but not allowing us to improve on the property of the concrete, Portland cement. But it's been done by the French and German people. Here's some example to show you. about the new materials. Ultra high performance fiber reinforced concrete is being done in this case in the South Korea, a bridge, because look at how thin that is. See how thin that is? It's extremely very thin. It's less than an inch that bridge, and it's a pedestrian bridge. It looks very pretty, and it is very efficient. Footbridge. 5 countries are allowed to produce this kind of cement. One of them, United States, Germany, and France. Of course, and if you want to build anything from this materials, then you have to have you bring the people with the materials to build it for you. They are not going to let you, get the materials by yourself and do it, because this is still top secret. There's other additional footbridge, and that's it. You can see how pretty that is. And in the United States, what we did is that we have some collaboration with MIT. We are the first people to produce a bridge open for traffic, and that is in Washington, D.C., with the collaboration of MIT. The bridge is about 21 meters, about 60 feet, and approximately about 9 feet. So it is because it's still at the beginning. We don't believe what we're seeing. We don't believe that we get really that kind of strength, that kind of power on the concrete. So we do not believe it. So we're still cautious, of using this material. We were very cautious to use this kind of material. Now it can be also transparent, and the best you can see is this kind of beam. You cannot make the beam deflect with an Portland cement. Look how the deflection is here. Look at the deflection. You see it? It deflects, but there's no cracks. It's flexible. It is high strength. It looks like a steel. It behaves like a steel, but at the same time, it's a concrete. Doesn't have this kind of disadvantage of the steel. That is one of the best pictures you can keep it in your memory about this kind of material. That is the best performance of that kind of material. Deflect, but there's no snapping in this case. Also in New York, we use ultra high performance fiber reinforced concrete to make chairs. So chairs made of concrete like this. You can see how thin that is. You can see how thin that material is. And that is, you can make furniture. You can make surgical equipment made of this kind of material. You can make bolts and nuts, and that's what we use in the Union Island. What we did is that we produced 6,300 with this kind of materials, with fiber plates. And think about the potential for this material in the future. And here in Canada, Calgary, in Canada, we use it for airport over there. And the thickness is less than an inch. Thickness of this one here is less than an inch, 20 millimeter. See how powerful that is. It's a concrete. It's not a steel plate. It's a concrete with high strength concrete, and with using ultra high performance fiber reinforced concrete. The performance of this material is still top secret. We do not really have it, widespread use. We are very careful to use it because we are still trying to understand the impact of this one in the long run. That's why we're still studying it, we're still improving it, and but we use it every now and then, and that's one of the use that we have for this kind of powerful kind of materials. With this, we reach to the end of this webinar. If there's any questions, you can send me through the chat message. I'll stay about 10 more minutes. Other than that, I will, thank you for attending this webinar and have a nice day.